Hey everyone, and welcome to The Explainer. Today we're doing a deep dive into the invisible architecture that essentially powers modern industrial automation. We're looking at the PCS7 signal lifecycle, and more specifically, we're going to unpack the incredibly complex translation process that takes raw physical industrial processes and turns them into sophisticated digital control logic. If you've ever found yourself wondering exactly how turning a physical valve flawlessly translates into a synchronized digital interface, well, you're absolutely in the right place. Let's get into it.
Okay, let's look at our roadmap for today. We're heading 6 main areas. 1. Hardware and software interface. 2. Digital and analog translators. 3. Diagnostics and signal status. 4. Hardware decoupling and synchronization. 5. Virtual testing and simulation. And finally, 6. The ultimate control blueprint.
To really understand this system, we first have to clearly define the core problem, and that is, hardware and software fundamentally do not speak the same language. Hardware is all about the physical stuff, right? Electrical currents, milliamps, voltage changes. But software? Software speaks in mathematical logic, Boolean values, scaled algorithms. To actually bridge this divide, we need a diplomat. And in the PCS7 system, that vital diplomat is the driver block. It acts as the critical translator between the raw physical hardware out in the plant and the system's actual technological application.
All right, moving right into Section 1, Hardware and Software Interface, Bridging the Divide.
Let's trace the entire life cycle here, because it's a pretty elegant loop. Down on the bottom left, you've got your physical sensor. It fires off an electrical signal into the hardware input module. This is exactly where it gets handed off to the input driver block, our translator we just talked about. Once that signal is digitized, it's pushed up into the operator station and processed by the technological control blocks. These are the guys doing the heavy mathematical lifting, like your PID control. The result? It's sent back down, processed through the output driver block, to turn it back into a physical command, and finally pushed out via the output module to the physical actuator. It's a continuous, perfectly managed loop.
That brings us to Section 2, Digital and Analog Translators, Decoding the Signals.
You know as well as I do, there's a messy reality to industrial automation. The control hardware receives data in a raw, unpolished hexadecimal format, something like 16-6600. But obviously, your control software and certainly the human operators on the floor can't run a plant staring at hex data all day. The system absolutely needs clean, scaled physical values to function. It needs to know that a tank is filled to exactly 5 meters. This critical, necessary work of taking messy code and turning it into tangible, real-world metrics, that's analog translation.
So this analog signal translation pipeline basically happens in 3 distinct stages. In stage 1, out in the physical plant, an instrument measures a level and sends a 4 to 20 milliamp current. Boom. Then, in stage 2, that electrical current hits the process image memory buffer where it's converted into raw hex data, say ranging from 16-0000 to 16-6000. Finally, in stage 3, the driver block grabs that hex data and transforms it into a scaled physical value from 0 to 5 meters. This specific conversion from a raw current to a measurable physical unit is all dictated by what's called the mode parameter inside the block.
Now, what's really interesting about this slide is how the P7 ANO block, the analog output, actively behaves to keep the physical plant safe. It isn't just blindly passing data. It limits outputs using 2 built-in switches. It can either rely on the physical range limits hard-coded into the hardware, or it can use custom scaling limits defined by the control engineer. And here's the kicker. If the signal breaches those defined safety limits, the block doesn't just crash or fail. It actively intervenes, it limits the value, and triggers a critical 16-78 status to immediately warn the system, hey, limits have been breached.
Moving on to Section 3, Diagnostics and Signal Status, the system's immune response.
In the real world, things go wrong. Wires break, sensors fail. So what actually happens when a raw value suddenly becomes physically invalid while a massive plant is operating at full capacity?
Well, that is exactly where the fail-safes kick in. Check out feature bit 30 on this slide. Instead of instantly crashing the entire process the second a wire snaps, feature bit 30 acts as a shock absorber. It literally retains the last known valid value for a set number of CPU cycles. This acts as a crucial buffer, holding the system steady and preventing a total system shock or a false trip just because a sensor flickered for a fraction of a second.
To keep a handle on all of this, the system uses what's essentially a signal status diagnostic dashboard. The absolute key takeaway here is that every single output in the system isn't just a naked number, it's a structured output. It always contains the actual process value plus one of these critical hex code statuses to flag issues the second they happen. A 16-80, you're good to go. A 16-78, the process is uncertain, maybe we hit a limit. And a 16-00 means the device itself is bad.
And I love this part because it brilliantly illustrates the separation of duties in the Pcs7 architecture. Look at the top user level. The control charts you're interacting with focus 100% on the process logic, opening valves, starting motors, the actual operation. Meanwhile, at the system level hidden below, auto-generated AT charts are handling all the complex hardware diagnostics behind the scenes. The driver generator compiler automatically maps hardware errors right to your channel drivers. That means control engineers don't have to waste their time doing tedious, redundant diagnostic programming. It's all handled.
All right, Section 4, Hardware Decoupling and Synchronization, the Translation Machine.
So, this right here is the translation machine concept in action. By using a symbol table, the automation program is completely 100% decoupled from specific hardware pins. Think about it. Instead of forcing an engineer to memorize that, say, a specific transfer pump is hardwired to an absolute memory address like IW512, the symbol table lets them just connect their logic to a simple symbolic name, like POCT01. If the physical wiring needs to change a year from now, no problem. You just update the table and your entire control logic program remains completely untouched. Huge time saver. But, as you know, decoupling requires absolute precision when it comes to timing, which brings us to process image partitions, or PIPs, and synchronization. The system reads and writes data based on very specific cyclic interrupt times. We're talking OB32 running every 1,000 milliseconds, or OB33 firing every 500 milliseconds. These execution times have to perfectly match the hardware update speeds. If they drift, you run the very real risk of read-write mismatches during data transfers, where your software is trying to read data at the exact millisecond the hardware is overwriting it. It's a synchronization tightrope. This sets us up perfectly for Section 5, Virtual Testing and Simulation, the virtual test bed. So the absolutely crucial point here is this. Because our driver blocks only ever interact with the process image memory buffer, and they never talk directly to the raw hardware, a simulation block can just casually step in and inject data directly into that same memory space. By simply doing an A-B swap right at the process image level, the downstream control logic just keeps happily operating normally. It literally never knows the difference between a real physical valve and a simulated one. It's brilliant.
And this is where engineers bring in tools like PLC-SIM as a virtual testbed. Through this interface, they can manually force binary states or punch specific hex values directly into the raw data addresses. What does that give us? It allows engineering teams to rigorously validate complex CFC logic, trigger alarms, and test all those failsafes in a totally safe, risk-free digital environment long before anyone even thinks about actual physical plant commissioning.
And finally, Section 6, the ultimate control blueprint, bringing it all together. This right here is the ultimate payoff of the entire PCS7 interface architecture. By isolating raw hardware, physical addresses, and device errors behind automated driver layers, control engineers can focus entirely on technological process logic, secure in the knowledge that every signal is scaled, synchronized, and safe. That is exactly what we're aiming for. Let's move to the next slide and see how this all builds into our final model. Think of the system like a series of defensive concentric rings. That outermost ring, that's the symbol table, abstracting away the exact memory addresses. Just inside of that, you've got the channel drivers, doing the heavy lifting of translating raw hex data into scaled physical units. Deeper still are the module drivers, providing an automated diagnostic shield to intercept and handle errors. And finally, protected securely in the very center of it all is the user program, the actual technological logic that runs the plant.
That really is the key takeaway from this explainer. When hardware and software are perfectly decoupled through these dedicated, shielded layers, control engineers are finally freed from the messy noise of the physical world. They aren't just managing raw signals anymore, they have the freedom to truly master the industrial process itself. Which leaves us with a pretty fascinating thought to consider as we wrap up. If we can perfectly simulate physical reality in a digital testbed today and seamlessly swap real hardware for virtual data, how might this total decoupling change the way we design the massive automated systems of tomorrow? Something to think about. Thanks so much for joining me on this explainer. Keep exploring, and I'll catch you on the next one.